Okay, thank you, Sergio. Today I want to briefly touch a couple of items in terms of, say, recent development in the area of nonlinear defined elements, and I think, in my very last slide, will be a nice expansion on the previous talk by Nicola. So stay tuned till the end of it. Okay, so I will start off with a very brief introduction on what's nonlinear defined element technology as opposed to linear defined element technology. Just one slide, and then, as I said before, touch on a couple of items which are currently being developed or which have recently been developed. I will show images based on, the Marc and Method defined element program and corresponding user interface. But as you mentioned, the technology is being used in many other products within the MSC software program portfolio. Okay, I always like to show the linear versus nonlinear differences based on a very simple structural element. I think all of us will have seen it once or many times based on a simple cantilever beam. If loaded at the very end in the vertical direction. So if the deflection is such that you can approximate it just by the deflection in the vertical direction only, then reduce the load, everything gets back to the original configuration. We call it linear. If you increase the load so that you also get an in-plane displacement, we basically call it nonlinear, and more particularly geometrically nonlinear. If you increase the load in such a way that you get, say, yielding of the material, if you're looking at a metal cantilever, then we end up with some permanent deformation, which is called plasticity, and the phenomenon is called physically nonlinear. And you may also have a situation where if you start deflecting the beam, then there is some other body underneath it, it touches it, and then you're basically solving a contact problem, and that's a problem with what you can call nonlinear boundary conditions. Two basic examples, inextensible bending on the left-hand side, so finite rotations, clearly a nonlinear problem, and then a basic cut volume simulation on the right-hand side where you have contact, plasticity, large deformation, large rotations, whatever, really nonlinear. So that's the type of problem which we will be focusing on. A pretty recently introduced algorithm to solve for contact problems is what we call a hybrid algorithm, and it basically tries to solve a number of known limitations, if you want, in an existing algorithm where we check for contact between nodes in your defined element model and edges or faces being touched, and we have tried to resolve those shortcomings by introducing a mixture of multi-point constraints and other penalties, with the idea that, okay, the user should not worry about penalty effect or stuff like that. So we have also added an algorithm which automatically adjusts the necessary penalty stiffnesses during the analysis to solve for those problems accurately. And along with that, we have also introduced a new way of solving contact problems with shell elements. Those of you familiar with shells know that we basically model a 3D space based on 2.5D representation, if you want. And within this finite element simulation, we are now able to reproduce it as a true three-dimensional body, but for contact only. So the actual, shell equations are still there and are still being used. So it's only for contact we can use it along with this hybrid algorithm. And I'll get back to remeshing along with contact in one of the next slides. A different thing is on both the solver and the GUI side having to do with units. Traditionally, our software has been, unit agnostic, so it was the responsibility of the user to say, okay, I'm going to use, newtons, millimeters, whatever. And we are in the process of moving towards a unit support, both in the GUI and in the solver, and it's happening in phases. And we have introduced model dimensions, so are we dealing with a full 3D model, with a planar model, with an axisymmetric model, and based on that we can limit, say, the choice, for instance, of boundary conditions or the data to be entered for your material behavior if you're talking about, say, plane stress type applications. And we also have already introduced in the database of our GUI the quantity type, so are we dealing with something with a unit of length, the unit of stress, stuff like that. And in the latest release to be, I hope tomorrow, we'll have also so-called table-dependent variables. And those of you who are a little bit familiar with the use of tables, I've added a simple example. If you want to prescribe your, say, prescribed displacement based on time, like a function of time, linearly 5 times the time, then typically when using a table, we say, okay, the displacement is given by a factor times the table. Then you can say, okay, this factor is 5, my table is 0 to 1, and then basically my factor has a unit of length, or the other way around, and that's possible now with the latest version. We can also assign the unit to the table itself, and it has quite some impact on the use of tables within your workflow. Which we have simplified, we introduce new options to easily create and assign those tables. So depending on the, say, the application range, is it a boundary condition, is it a material property, is it the most of the content, or things like that, we filter the right type of tables for you. And whenever you have a long list of tables already in your database, we allow simple filtering to pick the right table much more easily. Then a totally different topic recently added is a new material model to simulate delamination. So typically in laminated composites, those materials along with special element types are being used quite a bit. And the request, particularly from the composite world, was there to enhance the material modeling, particularly for scenarios where you have so-called mixed mode delamination. So if you think of just opening your model in mode 1, that's one, say, extreme mode. You can also say damage it in pure shear mode, that's the other extreme. But quite often, and most of the time, you have so-called mixed mode delamination. And the models we had in the software till now did not provide you a lot of flexibility to model this mixed mode behavior. And for that reason, we've introduced a pretty modern model called the Troll model, which takes into account this mixed mode behavior with an additional parameters you can obtain from experimental data. This parameter eta is not supported in the GUI and provides as a fourth model on top of the 3 models we already had till now. There is an example, it's embedded in the user guide of the software. It describes how to model a so-called mixed mode bending test. It's a test where you can say vary your configuration and then say do the test such that either mode 1 or mode 2 is dominant, or that you get pure mixed behavior by the same, say, testing mechanism, but just by applying your loading in a different fashion. The model is available, simulation can be run based on the latest version, and on the right hand side you see the comparison between the simulation and experimental data published in literature. So available hopefully as of tomorrow in the new version of the software. I mentioned to come back to global remeshing. There's continuous efforts going on in this area, I should say. If you say remember the type of problem you're focusing on, being nonlinear, then for models where you have, say, truly large deformations, you can imagine that the shape of your finite elements during the analysis will become pretty bad. I mean, if you start off, say, with a hexahedral element or a nice tetrahedral element with all equal faces, you start deforming it a lot, then at some point they get distorted too much and you need to replace it or stop the analysis. And we have the option to, during the analysis, automatically replace the elements and map the solution state of the current solution onto the new mesh and then continue the analysis. That's what we call remeshing, and we aim to release significant improvements in the quality of the mesh, the quality of the solution if you have, say, multiple compact bodies to be remeshed at the same time in the version at the end of the year. Now, and one of the things, here's an example, you can imagine that if you look at the amount of information that at some point you have to start thinking of replacing your mesh. And one of the things we want to introduce is this surface refinement. And it's shown on the right-hand side for a 2D configuration. And you can see that we are able now to drive the mesh density such that along the surface, where you typically need quite some elements in order to describe the contact behavior accurately, while in the middle we can deal with a coarser mesh in order to end up with not too many nodes, decrease efficiency, and thus a long solution time. And that way we can both efficiently and accurately solve complex contact problems. And then the last topic, and again that's I think a nice extension of the previous one, the use of ODC technology in Marc and that. The idea is to use that technology to come up with a reduced order model which to some extent is comparable with a classical superelement. But this reduced order model is also able to deal with, nonlinear responses. So it's not necessarily a, pure linear superelement, but it can be trained also in interface. And you can think of advantages like being able to protect the IP if you have trained your model and deliver it as a reduced order model to your end user. And also if you have structures where you can use multiple such roles, at the end you may be more efficient regarding the analysis time. Probably best illustrated based on a model like the one over here, where you have some rubber isolators in some human structure, just as an example to give you the idea of how it's going to work. The idea is that for this model we are going to replace the rubber parts by reduced order models. So what we can do is pick such a rubber isolator, kind of find an element mesh, pretty coarse one here just for the demonstration purposes, and we can use to train it some what we call special boundary condition. We call this a wrong boundary condition, and we typically use it to train the model based on the interface node. So the nodes which we will use later on to stuck it into the residual structure. Based on the dimensions, I would say, you as a creator of the reduced order model should know what's the dimension and what's the typical application range, so how large can the displacements be of the interface nodes. You can set up the DOE space, and that's done based on using a library from ODC embedded with market method. So you don't need to go to the ODC software itself, but you can immediately generate this DOE space in Mentat itself, and then use this DOE space in your training runs using Marc. So Mentat will automatically create the necessary data for Marc. Marc will run all the training runs, and then we can export the data, both in terms of the force displacement type responses we get, as well as the mesh data. So how does my reduced order model look like? And that's a combined ROM representation is exported in this FEM format, also mentioned before, and that can again be used to import that reduced order model, like shown on the right hand side. So at the top we have the same isolator as used to train it, and then the one on the bottom on the right hand side shows another instance of the same ROM, but then translated in space. Of course, we can import it, 6 more times, and then translate and rotate it to get it in the position of the original, 8 isolators we don't have. And that way we are able to both train and consume the reduced order models. And say if you want to say ship those reduced order models to your customer having the same software, that's easy. He can say use it, but he does not have say insight into the original 5-element data being used to train that ROM. In this case, the price. So it's currently under development and scheduled to be released before the end of the year. And yeah, with that, I'm at the end of my presentation. I think if there are questions, there will be plenty of time in between, so feel free to comment if you want to know anything in particular. Thank you very much.